So this topic is a supplementary topic for the database design. Okay. So this is again database designing, but we look at it in a slightly different way, different aspect of database designing. And we call it data normalization. So what is mean by data normalization? So data normalization means organizing the data into relational model. So that is basically what we did in database designing as well. So that is why I told you that this is also looking at the database designing, another aspect of database design. Okay. So the objectives of database or data normalization is number one, reduce the data redundancy. So redundancy means duplicate. So we want to eliminate or at least reduce same data appearing in different places. So different tables, same data. That is headache. Why is it bad to have the same data in multiple places? Two reasons. One is it take additional storage because same data is in two tables or three tables. So the second issue is it make it inconsistent data. Sometimes you update one table, but not the other places because the same data is in multiple places. Right? Like your name. So the government keep your names in multiple places. So ID card department, so they keep your name. Driving license, they keep your name. Education department keep your name. Sometimes there's inconsistency in your names. But if they all refer to one place as your name, there's no such issue. Storage wise, they don't have issues. And in case you want to change your name, you just change that place. Otherwise, you need to inform ID card department and get a new ID, get a new driving license. Maybe you need to change your name in your certificates, educational certificates. It's a headache, right? So therefore, we want to, if not eliminate, at least reduce data redundancy. The second objective of data normalization is better data integrity. So integrity means relatedness. So there should be proper relatedness between one data to the other data. Okay. So when you do proper data normalization, the integrity is also improved. Okay. Right. So let's look at some of those issues. So these are two tables. Right? Birth certificate, driving license. So birth certificate ID, driving license ID, the primary key in this table. So here you can see we have an entry called Kapila Silva. So here there's another entry called K Silva. Possibly these two entries refer to the same person. We don't know. Maybe. Okay. And you can see this is 1919 10 2. This is 1990 second to 10. Maybe the formats are different, same date of birth. We never know. Right? Still, just because the date of birth is the same, name is the same, still we can't say whether they are the same guys or different guys. So likewise, there are a lot of confusions. Right? A lot of confusions. And of course, you are keeping the date of birth in multiple places, keeping the name in multiple places. Okay. Sometimes we are not very sure whether they are those records related or not related. So much of confusions, waste of storage, and so on. So the objective of data normalization is as much as possible identify these issues and eliminate. Okay. So once you do the data normalization, the result is normalized ER model. That means you have eliminated as much as possible the redundancy and you have improved the data integrity. Right. How do you do data normalization? There are two ways. One way is now once you understand data normalization concept, that is what we are going to do today. Right? Once you understand it, when you do the designing, you will apply your understanding. Now, last time we did the database designing without thinking about data normalization. But after today, now today we are going to finish data normalization. So then when you do the designing for another database, you already know database normalization concept. So that you will use it in your designing process. So that will result in a better design. Okay, that will result in a better design because you know the data normalization concepts, you will naturally use it. Okay, so that means your design is complying with data normalization. So the second aspect is after doing your designing, of course, you know the data normalization concepts also. So therefore, you will, as much as possible, you will apply data normalization concepts in designing. But after the designing is finished, you can review your design against normalization concepts. And if there are any issues, you can fix it. Okay. So you will naturally use data normalization concepts in designing. And after the designing also, you can use normalization concepts and review it. Okay. So if you are a good designer, usually when you go into the review stage, usually you don't need to do anything. It's already normalized, but we all can make mistakes. So therefore, it's always good to double check whether your data is properly normalized. Okay. So in your exam questions, mostly they check the second approach because it's MCQ. Right. If it is essay paper, of course, they could have given you this kind of questions. Design it up with data normalization concept. Because you have a MCQ, they will give you set of tables and ask you which normalization form is failed, is it properly normalized, if normalized to which level. Okay. If you have any questions, you can ask. This is not an easy topic. At the same time, this is not a difficult topic. Only thing is you need to understand seriously. Okay. Right. So data normalization process. Now you know what is data normalization and why do we do this? Now let's see how to do it. Right? What, why, how. So data normalization process is a sequential process. So that means we do first normal form, check whether it's first normal form, and if not, fix it. Then you look at whether it's in second normal form, if not, fix it. Then third normal form, then boycott normal form, and so on. So you need to do it in sequential. You can't just randomly take third normal form and check whether is it in third normal form. No. Before that, you need to check what first and second. It's a sequential process. Okay. Right. So before moving into how to do this, let's discuss few theoretical aspects behind data normalization. There's a theory which is related to the relational algebra and relational theory. By the way, your next topic is relational algebra. So the two main concepts are atomicity of a data and functional dependency of a data. right? So especially the first normal form depends on this atomicity of data. Second and higher normal forms depends on functional dependency of data. What is mean by atomicity of data? You know what is the meaning of atom, right? Can someone tell me what is mean by atom? Anyone? What is mean by atom? When someone say atom, what comes to your mind? The meaning. I mean the literal meaning, right? Not chemical meaning. And in
Smallest.
small, not really. So in English, there's adjective called atomic. Atomic. Of course, one meaning is related to atom, but there's another literal meaning for atomic. Sometimes, yes, for small things also we say atom, right? What is the singular word? Paramanu. Parama anuva. Now, can you think of that? I think it's a good word. Usually, singular terms are really bad, but for this one, whoever gave this name he has thought about it and given a proper name. Parama anuva. Parama anuva. I think Parama Satya එහෙම කියලා තියෙනවා නේද? පරම අණුව කියන්නේ ඊට වැඩිය අණුවක් නැත. ඊට වැඩිය පොඩි අණුවක් නැහැ. ඕක තමයි අපිට දකින්න තියෙන අණුව. ඕක කඩන්න බෑ. That means you can't break it further and look at sub atom. You can't break it further and look at sub atom. This is the smallest part. So basically, it means you can't break it further. Okay, you can't break it further. So if you look at, say, sodium, piece of sodium, you can keep breaking. And what is the smallest unit? Atom. So your piece of sodium is collection of atoms. Okay, collection of atoms. Okay. Then someone, if you are a critical thinker, sometimes you might ask, we can break atom further, right? Protons, electrons, but that is different type of breaking. There is different type of breaking. So sodium, piece of sodium consists of sodium atoms. Piece of calcium consists of calcium atoms. Okay. The nature of sodium is in sodium atom. Right. So therefore, what is meant by atomicity? You can't further break it. You cannot further break it meaningfully. Right. So this is non-atomic field. Why? When we say skills, person might say, okay, I have the Java skills, Python skills, PHP skills. Another person will say, I have the C Sharp, C++, Java. Another person will say, I have HTML, CSS, JavaScript. So therefore, skills is not atomic. But maybe your email address, if you have only one email address, or your login name, it's atomic. Your ID number, atomic. Your date of birth, atomic. So atomic doesn't mean unique, primary key. Atomic means it has only one value, date of birth. You can't have two date of births. You can't have two genders. Those fields are atomic. But there can be a field where there's a possibility of multiple values. So then those fields are not atomic. Even contact number can be non-atomic. If someone will say, I have two contact numbers. Right. So first normal form is related to atomicity of data. Second and higher normal forms depends on functional dependency of data. Actually, understanding atomicity is easy. This is the real challenge. Understanding what is meant by functional dependency. By the way, after doing logic today, we start relations and functions also in maths. So there also we use the word relations and functions. Okay. Right. What is meant by functional dependence in database? This is not maths. So functional dependency describes the relationship between attributes. This is database terminology. Right? So we can say that A attribute functionally determines B attribute. A functionally determines B. Okay. I think one of you have not mute your microphone. Okay. So let me mute everyone. Right. So what does this means? A functionally determines B. So then what is mean by A functionally determines B? So A functionally determines B means for each unique value of A, there exists only one corresponding value of B. So this is also somewhat related to atomicity, but this is slightly different concept. So when do we say that A function determines B? For one value of A, there must be only one value of B. Otherwise, A doesn't function determine B. And also this is related to the concept of key. Okay, concept of key. Atomicity has nothing to do with the key. Right? For example, date of birth is atomic field, but date of birth may not be the right key, right? Because different records may have the same date of birth. So let's look at it a little bit more detail. Right? A functionally determines B. Well, a value of A is associated with exactly one value of B. So that means when we know value of A, it must correspond to only one value of B. Now you can see only one value of B. Value of A correspond to only one value of B. Value of A correspond to only one value of B. Value of A correspond to only one value of B. So this is 5. So here we can say A functionally determines B. But then what about this? For value of A, there must be only one value of B. But you can see for value of A, for A1, there are two values of B, B1 and B2. So this is not, we can't say A functionally determine B. Okay. We cannot say that A function determines B. And this is fine. A2 says B2, A3 says B2. That is fine. But only thing is for one value of A, there must be only one value of B. Nothing else. Nothing else. Here it has been violated. Okay. So just when there's a definition, you must only concentrate on that definition and nothing else. Because if nothing else is important, that we will include that into the definition. Sometimes what happens is when you are given a definition, you add some other things from your mind to that definition and you think that that is the definition. That is your problem. That is your problem. That means you add some unnecessary things that you think it should be included to definition or you assume. No, that is not the case, right? This is science, formal science. If it is, if you need to consider that, of course, we will add that to the definition. So therefore, it's very simple definition. A functionally determines B if for one value of A, there is only one value of B. Simple as that. So don't think anything else. If you think anything else, that means your problem. So let's take more practical example. So if you know ID number of a student or person, you know that there must be only one name for that person. So I'm not talking about nicknames and so on, official name, the birth certificate name. Your birth certificate doesn't have two, three names, right? So therefore, if you know the ID number, there must be single name for that ID number. For one value of this, there's only one value of that. So therefore, we can say ID number functionally determines name. So this is the district that person has registered for elections and so on. So then for one ID number, there must be only one district. Okay. One ID number, there's only one district. So therefore, ID number functionally determines district. So if I know the ID number, I can tell, okay, this is your district. You are registered for elections and so on. Your residential district. But can we say like this? If you know the name, can you say that I can definitely say, uniquely say ID number? No, because two people may have the same name, two or more. Right? So there can be another Nimal Pereira with the same ID. So therefore, just because you know Nimal Pereira, it doesn't mean you can say uniquely what this is the ID number. So therefore, name does not functionally determines ID number. Name does not functionally determine district because there can be two people with same name in the same district or different districts. So therefore, these are not functional dependencies. Okay, but these are valid functional dependencies. So this functional dependency is a theory. It's a theory. It's part of the relational theory. So that is why this topic is sometimes harder for some students if you are not very good at abstraction. Think at abstract level. So we can extend the concept of functional dependency. Now, so far we discussed at attribute levels. One attribute functionally determines another attribute. We can extend it to entity levels. We can say whether a particular entity functionally determines another entity. Right. So that means, does employee entity functionally determines department? Let's assume for one employee, there's only one current department. Always one employee is assigned to one department at a time. So then we can say employee table or employee entity functionally determine department, but not the other way. If you know the department, it doesn't mean that you know the employee. But if you know the employee, you know the department. Right? If you know the student, you know the course. Assuming that student is assigned to only one course. Of course, if student can enroll into multiple courses, again, this doesn't work. Actually, that should be assumption here, right? Assume student can enroll into one course. But it doesn't mean that you know the course. It doesn't mean that you can define the student. Okay, maybe we can write it as within bracket, right? Otherwise, you get confused because student can, if student is in multiple courses, we can't say that. Okay, so let me write it as an assumption. Student enroll to only single course. Otherwise, you will get confused. Okay. Okay. So that means we can extend this concept into entity levels as well, not only for attribute levels. So basically, if it is a one-to-one relationship, one-to-one, or many-to-one, it is function that functional dependency exists, but not one-to-many, not one-to-many. If course can have many students, so then we can't say course function determines student. But if student can study only one course, yes, it is functional dependent. Or student can have only one course and course can have only, oh, that is not the case. So that means one-to-one, many-to-one, preserve functional dependency at entity level, but not for other things. Okay. Right. So now we move on to another theory aspect. Armstrong axioms of functional dependence. Remember, this is related to functional theory. Remember, last few weeks we discussed about Boolean algebra. So today we will start discussing, not today actually, formally next class, relational algebra. So today we look at the relational theory, the basics of relational theory. Next class we will move on to the relational algebra. Right? Boolean algebra in maths, relational algebra in databases. And the funny thing is, in order to understand Boolean algebra, we use sets. In order to understand relational algebra also, we can use sets for some extent. So that is why I always telling you that sets is the one of the most important topic, especially for IT students. Right. So let's look at what are those axioms. You know what is axiom is, right? What is the axiom? Just tell me what is the axiom. In simple one or two words, explain what is mean by axiom.
A postulate.
So that is synonym. I asked you to use in one or two statements, explain it. I'm not asking for synonyms. Or I'm not asking for the singular term.
uh, that in mathematics that uh, considered as uh, logically true.
Okay. Cannot break in, sorry, refers to a statement that is accepted as true without proof. So that is not a very good definition actually. So why do you want to accept something without proof? That you need to explain. Is it because it's God's word, it's mentioned in a all book? So that you need to explain. Why do you accept it without proof? Why do we accept something without proof? This is science, formal science, right? So if you answer that question, that is fine. So you're almost there. I'm not saying that your statements are wrong. I need a little bit more explanation. That's it. Yeah, self-evident. So that is the word, right? Self-evident, obvious. If something is obviously true, right? Obviously, logically true, then you don't need to prove it. Actually, when obvious things we can't prove it, right? that only you need to think about it and see. Right? Think about it. Of course, until it is obvious to you, you can doubt it. You can say no. Once it's self-evident, then you can use it. So that is what is called axiom. Okay, axiom. So actually, we can't prove it because it's obvious. Okay, because it's obvious. Right. So Armstrong, a person who came up with few axioms, about one, two, three, four, five axioms. I think five or six. I have given you only five. Right? We call them those Armstrong's axioms in functional dependence. Okay. Right. So let's assume A, B, and C be subset of attributes of relation R. Say we have relation or table R. A, B, and C are subsets of attributes of relation R. So the first axiom says A functionally determines A. Okay, A functionally determines A. And if B is a subset of A, then also A functionally determines B. Right? A functionally determines A. And if B is a subset of A functionally determines B also. Now, can you think about it? So if I say ID number functionally determines name, you can see it, right? You can feel it, right? Correct, right? Because for one ID, if I know the ID number, I can tell you the name. If you don't know, you can ask from the government, right? ID department or whatever, they will say this is the name because for one ID number, there's only one name. So this says something like this: ID number determines ID number. That is obvious. Yeah? If you know the ID number, you know the ID number. If you know the name, you know the name. If you know that name is Nimal Pereira, you know that name is Nimal Pereira. If you know the date of birth, you know the date of birth. So therefore, that is obvious, right? Obvious. So that is why we say it's axiom, right? So just because I'm saying obvious, don't accept it. See whether you also feel like it's obvious, okay? Until you feel like obvious, don't accept it. And what happens if B is a subset of A? It's something like this. Say ID, comma, name. Functionally determines ID. Correct, right? If you know ID and name, you know ID because B is a subset of A. And again, I can say ID, comma, name functionally determines name. Say ID, name, comma, department functionally determines name, comma, department. Or ID, comma, department. Or ID, comma, name. Because you know all three combination. So then, of course, you know any of the combination or any of the individual because you know all three. And so yes, these are very simple, but you must be really serious about those. Okay, really serious. So you know that at the end, only about less than 300 students get the degree. So a lot of students think that this is nothing, right? මේවා මොනවාද තියෙන හැමෝම ඩිග්‍රී ගන්න. හැමෝම ඩිග්‍රී කරගෙන එළියට යන්නේ. හැම ඩිග්‍රී කරගෙන යන්නේ නැහැ. බහුතරය. කොහෙදී හරි ඉර වෙනවා. පේපර්ස් වල. කොහෙදී හරි ඔයාලට එපා වෙනවනේ මේක කරගන්න බැහැයි කියලා. කියන්නේ සීරියස් කියලා හිතුවට සමහරවිට සීරියස් මදි. Right, so that is our first axiom. A function determines A or A function determines B given B is a subset of A. So that is called reflexivity. So the second functional dependencies related axiom is called transitivity axiom. See whether is it obvious to you, is it self-evident to you? You need to think about it and see whether is it correct. Do you feel like it is logically correct? If A functionally determines B and B functionally determines C, then A function determines C. That means for one value of A, if there's only one value of B, for one value of B, if there's only one value of C, that means for a given value of A, we can unique specifically say this is the value of C. That means when you know A, you know C specifically, without any doubts, without any ambiguity. If this is the case, so this is called transitivity. Transitivity. You know what is the meaning of transit, right? So sometimes when you go from Colombo to say Tokyo, so sometimes you directly go there. Sometimes maybe there's a transit in Singapore, transit flight. So there's a transit, or maybe there's a transit in Dubai when you go Rome. So transitivity means if A determines B and B determines C, then A determines C. Is it self-evident to you? ඒක එහෙමයි කියලා තේරෙනවද? Take a database example also. So if you know the employee ID, right, you know the department ID. Assume that one employee work only for one department. If you know this employee ID, you know the department ID. And if you know the department ID, you know the department name. So that means if you know the employee ID, you know the department name. Got it? Right. Third one. Actually, these two are the most important for us. These two are the most important for us. But we will look at the other three also because those are also very important. It improves your logical thinking. Okay. Your intellectual capacity of looking at things, analyzing things. Right. So the third Armstrong axiom says, if A functionally determines B, and if A functionally determines C, then A function determines B, C. Okay. If A function determines B, and if A function determines C, A function determines B and C combination. Okay. It's like your ID determines name. ID determines date of birth. So then I can say ID determines name and date of birth. Obvious. That is, of course, if it is obvious, that is why we say it's axiom. But I don't know whether it's obvious for you. You need to think about it. Okay. So BC means BC combination. If we know ID, we know name and date of birth combination because ID determines name, ID determines date of birth. That is called union. Axioms related to unions. Then we have the augmentation axiom. If A functionally determines B, say we have another attribute called C, A comma C functionally determines B comma C. Okay, A comma C function determines B comma C. That is called augmentation. Okay, for example, say ID determines name. So then ID comma email determines name comma email. Okay, let's take another example. Say name determine email. then name comma date of birth determines email comma date of birth. If this is the case, okay. If this is the case, but usually name doesn't determine email, okay, because there can be same name with different people. Therefore, this is not a very good example anyway. But the previous one is correct. Okay. Say department ID determines department name. So then department ID comma manage ID determines department name comma manage ID. Okay. Right, so that is called augmentation. Final one is projectivity. If A determines BC combination, so that means A determines individually B and individually C. Right? If ID determines first name, comma last name, I can say ID determines first name, ID determines last name. Do you have any doubt about it? Do you have any doubt about it? Okay. So that is called projectivity. But remember, we are more interested in these two. Okay. But there are some past paper questions. You need to have understanding about these things to get the correct answer. Because this is abstract area, examiners can give you really challenging questions to filter out the best abstract thinkers. Because this is a theory, abstract concept. Very, very important concept. So sometimes you may not still feel like this is important, right? සමහරට ඔයගොල්ලෝ තාම මේක හිතෙන්නේ නැහැ. මේක ඔය තරම් වැදගත් මේ යකා මේ දැන් පැය භාගයක් විතර දිස කියවන්නේ කියලා. මේක වැදගත් නෙමෙයි, පුදුම වැදගත්. පුදුම වැදගත්. මේවයින් තමයි මිනිස්සු රීසන් අවුට් කරන්නේ සහ රීසන් අවුට් කරනේම වරද්ද ගන්න. සමහරු කියන්නේ මොන හරි ප්‍රශ්නයක් වුණාම මගේ ග්‍රහය හොඳ නැහැ. එයා හිතන විදිය. ඊට පස්සේ ඉස්පිරිතාලේ ගිහිල්ලා බෙහෙත් අරන් එහෙම ඇවිල්ලා හොඳ වෙලා කියනවා. මේ බෝධි පූජාව කරපුවත් මේ මම හොඳ උනේ ටක් ගන්න. මේක ඉස්පිරිතාලේ ගිහිල්ලා සේලයින් දීලා ඔක්කොමත් කරලා මේ ගෙදර එනවා. මේ බාරයක් වුණා. එයා හිතන විදියනේ. එයා හිතන්නේ x නිසා නෙමෙයි උනේ y නිසා කියලා. ඒකට අපි බලන්න y අයින් කරත් මෙයාව හොද වෙනවා. ඒතර එහෙම වුණ කරන්න අපි දැන් මොකද්ද? මුංග ඉස්පිරිතාලේ නවත්තන්න නැතුව බාරයක් විතරක් කරලා තියන්න ඕන ගෙවල් වල. එහෙම කියන අය. පෞගී කාලේ කොරෝනා ආපු වෙලාවේ හරි චූ ගිහිල්ලා බය වෙලා පෝලිං වල ඉඳලා ඉන්ජෙක්ෂන් ගහගත්තා. දැන් කට්ටිය කියනවා මේක හඳ නෙමෙයි මේ හරි ප්‍රශ්නේ මේ ඉන්ජෙක්ෂන් එකේ. ඔය ඉන්ජෙක්ෂන් එකේ සයිඩ් ඉෆෙක්ට්ස් තියෙනවා. හැබැයි ඊළඟ පාර වසංගතයක් ආව ගමන් ඒක ඕකම අල්ලන් ගිහිල්ලා ඉන්ජෙක්ෂන් නොගහන පොලිමේ තියන්න ඕන. බයිලා ගහනකොට. ඒ රීසන් අවුට් කරන විදිය ඒගොල්ලෝ. ඕක තමයි මේ මිනිස්සුන්ට තියෙන වාද විවාද ඔක්කොම. මේක හන්දද මේකුනේ මේක හන්දද මේකුනේ මේක හන්දද මේකුනේ මේක හන්ද මේක වෙලාද මේකුනේ නැත්නම් වෙන එකක් හන්දද. මේක විතර දෙකම රීසන් එක. නැත්නම් අර රීසන් කම්බිනේෂන් එකෙන්ද මේකුනේ. ඕක හොයාගන්න බැරි වුණා මිනිස්සු කන්ෆියුස් වෙලා යනවා. මිනිස්සු පිස්සු ගෙලින්න පටන් ගන්නවා. මිනිස්සු මීහරක් වගේ හැසිරෙන්න පටන් ගන්නවා. So therefore this is very important. logic විතරක් නෙමෙයි මේ ඔක්කොම එකට එකතු කරාම තමයි ඔයගේ විචාර බුද්ධිය හැදෙන්නේ. මේකත් එක පැත්තක් රීසන් අවුට් කර. ඩිපෙන්ඩන්සි හොයාගන්න එක. So I'm not criticizing, right? මම මේ කාවත් විවේචනය කරනවා නෙමෙයි. I'm telling you the reality. සමහර වෙද මහතුරු ගාවට කියනවා දෙනවා මොකද්ද? එන වට්ටෝරුවක්. ආරව තියෙනවා, මේවා තියෙනවා, අනිත් ඒවා තියෙනවා. මේක කසායක් හදලා බොන්න. මේක හැබැයි if you go to the western medicine ඔයාලට හරියටම දෙනවා මෙන්න මේක තමයි බෙහෙත. ඔයාලට ඇමොක්සිලින් කරලා දෙන්නේ. ඇමොක්සිලින් දෙන්නේ. පැනඩෝල් දෙන්නේ. ඒගොල්ලෝ මොකද කරන්නේ? මේවයි තියෙන ඩිපෙන්ඩන්සි හොයලා හොයලා බලනවා කොයි එකෙන්ද මේක උනේ කියලා. අන්න ඒක ඔයාලට දෙනවා. අර හොයාගන්න බැරි එක නම් මොකද කරන්නේ? වට්ටෝරුව දෙනවා වට්ටෝරුවෙන් මොන මගුලෙන් වෙනවද කියලා දන්නේ නැහැ. වැඩේ වෙනවා. වැඩේ වෙනාට වට්ටෝරුව දෙනවා. වට්ටෝරුව මාරු කරාට පස්සේ හරියන්නේ නැහැ. ඒක එක එක දිලා ටෙස්ට් කරන්නේත් නැහැ. ටෙස්ට් කර කියන්නේ විද්‍යාත්මක අය ටෙස්ට් කරන්නේ. ඒක ටෙස්ට් කරන්නේත් නැහැ. වැඩේ හරියනවා. ඒකම දිදී ඉන්න වට්ටෝරුව. Right. So these are called Armstrong axioms. These are super important, not only for databases, right? Reasoning out what is the exact reason. දැන් මේ දවස් මිනිස්සු කියනවා නේද මේ රට බංකොලොත් උනේයි කියලා නේද? කොච්චර අන්දනවාද මිනිස්සු රට බංකොලොත් උනේ මේක නිසායි කියලා.
So what is the context in functional dependency? Is it mathematics or database?
It's both mathematics and database. Of course, mathematics is mathematics and logic. Remember, maths is not logic, logic is not maths. Maths and logics are related. And database is application. Database is not a formal sort of a science, right? So therefore, we apply logic, mathematics in database. So therefore, the applications are in databases and everywhere in real world reasoning and so on. But this concept is partially mathematics, partially logic. And of course, maths has connection with logic. Okay, logical thinking. This is basically part of logic or formal logic. But this is not Boolean logic directly. This is relational
Okay, sir.
algebra, not Boolean algebra. Okay. Right. So these are some examples for reflexivity. Okay. So we have already discussed this. Transitivity. Student ID determines department ID. Department ID determines department name. So therefore, student ID determines department name. Okay. So this is union. Student ID determines name. Student ID determines course. So therefore, we know the name course combination for this student if you know the student ID. Assuming one student is doing one course. Okay. Again, under that assumption, so augmentation. Student ID determines name. Then student ID course ID determines name course ID. So this is another example. See whether you can understand this. This is with database table. What is augmentation says? If A determines B, then AC determines BC. Okay. It doesn't say that AC determines B. Okay. That is not correct. AC determines BC. Say this is my set of data. Value for A, value for C, value for B, value for D. Okay. Can we say that A determines B? A determines B. For one value of A, there must be only one value of B. Yes, right? 1 is 5. Yes, 1 is 5. 1 and 5. Correct? 2 and 6. Yes. 2 means 6. If 2, 6 and 2, 7, then we can say A determines B. But here you can see A determines B. Yes, correct. Yes. So this data set satisfies A determine B. ඒතර කාටද කියන ඩුප්ලිකේට් මම කියන්නේ ඩුප්ලිකේට් වලට කවන්නේ මේ තියෙන්නේ A කියන එක දන්නවනම් B එක දැනගන්නවා වෙනස් වෙන්න බෑ එක එක සැරේට Right. So now let's have C. C has for these four records here X, here Y, here X, here Y. Now then AC, that is 1 and X combination, determines B and C combination. Okay. That is X and 5. Again, if you have 1 and X, it must be X and 5. 1 and Y, it must be Y and 5. 2 and X, it is X and 6. 2 and Y, is it Y and 6? Okay, so therefore, yes, AC combination determines BC combination. But can we say that AC combination determines B? ඔක තමයි හරියටම තේරුම් ගන්න. AC. This data set is not very good for that because we have only one such thing, right? Let's take a different set of data. Here we have, right? AC. Yes. So you can see AC, we have 1x, right? Which is 5x. And here we have AC1y, but that is different data set, right? Yeah. So that is not a good data set to explain that. Right. A determine B. Okay. So other way. Can we say that A determine BC? If A determine B, can we say that A determine BC? No. Why? Because 1 determines 5. Yes. 1 determines 1 is mapped to 5. Correct. But can we say that A determines BC? Because BC combination is different now. This is X5, this is Y5. So 1 is mapped to X5, 1 is mapped to Y5. So therefore, you can't say that just because A determine B, that means A determine BC. එහෙම කියන්න බෑ. ඒක තේරෙනවද? අපිට එහෙම හිතෙන්න පුළුවන් නේද? If A determines B, A determines BC කියලා. මොකද A නේ B determine කරන්නේ. ඒක හන්ද A determine කරනකොට BC නෑ. එහෙම determine වෙන්නේ නෑ. Because 1 is mapped to X5, 1 is mapped to Y5. So that means that is not functional dependence. So functional dependency එක නෑ මෙයා map වෙන්න ඕනේ එකම value එකට විතරයි. දැන් value දෙකකට map වුණා. Value දෙකකට map වුණා කියන්නේ මෙහෙම ලියන්න බෑ. But we can write AC determine BC. ඔන්න හොඳයි ලියන්න. Because then that is fine because AC combination is this and BC combination is this. And AC combination is this, BC combination is this. For one combination, sorry, this is 1y. For one combination, there's only one value. This is a different combination, different value. Another combination, unique value. Another combination, a unique value. For one AC combination, there are no two BC combinations. But if you take A determines BC, that doesn't work. Just because A determine B, you can't say A determine B. දැන් තේරෙනවද අපි මේ ලියන සමහර ඒවා obvious ලිව්වට ඒ obvious අතර තමයි දුන්නේ. හරි axioms කියලා. නමුත් මේ axioms අතර කොහෙවත් නැහැ A determines B implies A determines BC කියලා. මොකද මෙහෙම වෙන්නේ නැහැ. එතකොට ඒකයි අපි කියන්නේ මේ කතන්දර හරි වැදගත්. මේවා හරි. හැබැයි මේ වගේ ඒවා හරි කියලා ඔයාලා හිතන ඒවා හරි කියන්න එපා. For example, there's nothing called A determines B means A implies BC. No, it is AC determines BC. Okay. දැන් අපි තුමු රිසර්ච් එකක් කරනවා කියලා PhD එකක් කරනවා කියලා. ඉතින් PhD එක කරන්නේ මේ හොයන එකනේ. නේද? බෙහෙතක් හොයා ගන්නවා කියලා හිතන්නේ. දැන් මිනිස්සු බෙහෙත් හොයන්නේ රිසර්ච් කරලා. ඉතින් මේ මිනිස්සු තනිකර ඔළුවේ යන්නේ මේ ඩිපෙන්ඩන්සි. මේකට මොකද්ද හේතුව? ඊට පස්සේ මොකද සොලියුෂන් එක? හැමතැනම රිසර්ච් නෑ නේද? යුනිවර්සිටි වල රිසර්ච් සෙන්ටර්ස් වල ඔය හැම මිනිස්සුම කරන්නේ මොකද්ද මේ? ඔන්න ඔය ඩිපෙන්ඩන්සි එක ගහන ගේමක් මේ කරන්නේ. ඉතින් ඒක හොඳට සෙට් වෙන කට්ටිය තමයි රිසර්ච් වලට යන්න ඕන. හරි අයින්ස්ටයින් ඉඳලා හැමෝම ඇයි මෙහෙම වෙන්නේ? හොයාගෙන ගිහලා අයිසොලේට් කරලා ගන්නවා මෙන්න මේක හන්දයි මේක වෙන්නේ. ඒක අයිසොලේට් කරගන්න හොඳට වඩ ෆන්ක්ෂනල් ඩිපෙන්ඩන්සි ඔළුවේ තියෙනවා. ලොජිකල් තින්කින් එක. ඒක බැරි කෙනා හැමදාම ඔය වෙන වෙන බයිලක ගහ ඉන්නවා. බුල් කියලා ගලී ඉන්නවා. ඒගොල්ලොත් එක්ක කතා කරන්න ගියාම අනිත් මිනිස්සුන්ට පිස්සු හැදෙනවා. ඒක හොඳ වැඩේ කතා නොකර ඉන්න එක. මොකද ලොජිකලි අපිට තේරෙනවා මේක මෙලෝ රහක් නැහැ. මෙලෝ කනෙක්ෂන් එකක් නැති දේවල් මේ දොඩවනවා. හරි. එකපාරක් මේක කියනවා තව පාරක් මේක කියනවා. ඉතින් එහෙම කතා කර කර ඉන්න පුළුවන් පැය ගණන්. හැබැයි ඒක නිෂ්ඵල කතන්දරයක්. ඒකට එයාට කියන්න දෙනවා ගිහිල්ලා ලොජික් ඉගෙනගෙන එන්න. ආම්ස්ට්‍රෝං ඇක්සියම්ස් එක ඉගෙනගෙන එන්න. මෙහෙම කියන්න බෑ ඔයා කිව්වට. ඒක සමහර මොකක් හරි කතා කරගෙන ඉඳලා ඒක තව එකක් එකතු කරනවා නේද? ඔක දැකගන්න දේශපාලන සංවාදවල එහෙම එකක් ගැන කතා කරලා ඊට පස්සේ ඒක තව එකට කනෙක්ට් කරලා කියන මේ දෙක හන්ද මේ දෙක උනා කියන. මේ දෙක හන්ද මේක උනා කියන. මේ දෙක හන්ද මේක උනා නෙමෙයි. Right. So this is an example of projectivity. A determines B, Z means A determines B and A determines C. If student ID determines name and department ID. So there's a spelling mistake, okay. Right. So if student ID determines name and department ID, we can say that student ID determines name, student ID determines department ID. Okay. So this example for that. Right, I am telling only Sinhalese. I use Sinhalese to additional things only. So therefore, it's not going to affect you. Okay, don't worry. I'm not explaining any academic things in Sinhala. So therefore, I only tell Sinhala. I use Sinhala only for additional or outside things only. So therefore, it's not going to affect you, right? Don't worry. Right. Don't worry. I'm not explaining any academic things in Sinhala. Okay. Right. Any political or any other additional things only, right? It's not going to affect you at all. Right. So what about this? Because some things you need this cultural background to explain. Okay. So can you understand this slide? This is related to the if A determines B, right? It doesn't implies AC determines B. This is another policy, wrong thing that some people believe. If when we say A determines B, they think that means AC determines B. Okay. But that is not the case. So just because A determines C, we can't say, sorry, A determines B, we can't say that AC determines B. Sometimes you may feel like it should be. But actually there's no such thing in logic, in functional dependencies. Okay. Look at the data and see yourself. So that means for one value of A, there must be a unique value of B, right? Yes. 1, 5. Now what happens? Sorry. 1, 5 and 1, 6. So that means, okay, so that data is wrong, right? I think this data is wrong. Yeah, 1 is 5, 1 is 6. No, that can't be the case, right? Okay, so let's say this is also 5. I think the data is wrong. Right. 1 means 5. 1 means 5. Mhm. There's a unique B. Okay, so this should be
So
something like
it's correct now.
this should be 2, right? Yes. Can you repeat?
Yeah, so for one value of A, there should be one value of B now.
Yeah, so therefore
So,
this data is not correct for A implies B, right?
yeah.
Because it says it's we start with A implies B. So therefore, let's say this is 1, this is 2. Okay. So then I think this data set is correct, not correct. Uh, Actually, I generate this data set from ChatGPT. ChatGPT has not, I assume that ChatGPT has generated the correct data set, but ChatGPT has not generated me the correct data set. Okay, so let me regenerate it. So let's ChatGPT. I think ChatGPT has either I have copy paste error. But this is not a tabular example. Rather, it has given me a different example. Okay, let's see whether this example makes sense. A implies B. That means if it is raining, the ground is wet. Okay. Let's say whenever raining, ground is wet. That is common sense, right? When it is raining, obviously ground must be wet. Now, can we always say that A and C implies B? That is when it is raining and ground is covered with plastic, the ground is wet. No, right? Because when the ground is covered with plastic, the ground can't be wet. Ground means the grass. So therefore, just because A implies B, we cannot say that AC implies B. Right? So it doesn't make sense. Right? So A implies B doesn't mean A and C implies B. Okay, so shall we ask it to generate data? Generate relational table, data table example. Let's see whether this makes sense. Okay, it's a big table. Okay, I think relational data.
So does that mean a PhD is a math-oriented thing?
No, PhD is all about researching and come up with new idea, new concept. It depends on the field, right? For example, you know that there are PhD for Mervyn Silva also, right? And there's our former speaker is still looking for his PhD, right? And he went to Japan also. So therefore, PhD is also business also, right? These days. So I'm talking about the valid PhDs, and it depends on your field. So basically, the idea about PhD is doing a research and come up with new finding, come up with new finding, which is
Okay.
useful to the humans, humankind. That is what PhD is. There's no exams in PhD. That is in general, right? So then there's something called honorary PhDs. Honorary PhDs. So to honor someone's work, the university can give a PhD, right? So that is different. So therefore, it's a broad area, right? But what I mean is the general PhD is you do a research and find new thing, new knowledge, which is useful. Then you are eligible to
Okay.
get the PhD. Okay. But again, you can see that it is subjective, not like a competitive exam, right? So you have a supervisor and set of people. If they are convinced, they give you the PhD. But you know that humans are humans, right? So people have some corruptions and blah blah blah. So therefore, one might say, okay, we are convinced he's good, his research is good enough. Then the university will say, okay, we offer the PhD. Okay, so
Okay.
therefore, let's not dig into those kind of controversial things. Okay, it is not like competitive A-level exams and you get A. Okay, so let's take this one. A implies B. 101 means yes. 102 means no. 103 means no. Okay, unique, right? So there's nothing called contradicting. So then can we say AC implies B? AC, that is 101 and no implies yes. Uh, okay, so I'll give you different examples and explain it later because otherwise we waste our time. Okay, because I think this generated data is not good, but definitely the concept is valid. The generated data set is not correct. Okay, so therefore I'll explain it maybe in the next class again. Okay, right. So, but anyway, you can't say that just because A implies B, AC implies B. Okay, just because A implies B, you can't say AC implies B. Just like that previous example, right? Raining and when the covers are on, you can't say now ground is wet. Because the second one might prevent the first one again. So therefore, when you combine that, it may not happen like that. ඒ කියන්නේ බෙහෙතක් තියෙනවා. ඒ බෙහෙත X කියන දේ තියෙනකොට Y එනවා. හැබැයි X සහ Z දැම්මම Y නොවෙන්න පුළුවන්. මොකද Y Z වලින් අර Y වෙන එක වළක්වනවා. Right? So the Z prevent Y happening. So then all of a sudden it doesn't work. So when you take X isolate, yes, Y happen. When you take X with Z, Y may not happen. Because Z may prevent Y happening. Okay, so therefore you can't always say that when A implies B, A and C implies B. Okay. AC implies B or A and C implies B. There's no guarantee. Okay. Right. So now we move on to our next concept, closure. Right. Closure. This is another abstract concept. So these are the junctions that some students start struggling. Right. What is mean by closure? Just like the functional dependency. Okay. Right. So what is mean by F closure? If everything that F functionally determined is called F closure. So what is mean by F closure? Everything that F functionally determines is called F closure. Right? And if X is an attribute, X closure is we represent by X star is set of attributes derived by applying Armstrong axioms. That means everything that X functionally determines is called X closure. Right? Everything that X functionally determines is called X closure. Okay, so let's take an example. So let's have a relation A, B, and C, or attributes or relations, because these are true for attributes as well as relations. So let's see, we have three attributes, A, B, and C. A function determines B, B function determines C. Those are given. So then the question is, what is F closure? This is not X closure, this is F closure. So F closure means all functional dependence. Okay, all determined things. So we know that A determines A, right? Why? Reflexivity axioms of Armstrong. So therefore we can say A functionally determines A. And again, we can say B functionally determines B. C functionally determines C. Do you agree? Because these are axioms. Obvious. Okay. So that is how you got these three. So F closure means you need to write down all the dependencies, functional dependencies. Write down all functional dependencies, F closure. So then they have given that A determines B. So therefore we can take that toss because it's given. They have given that B determines C. Therefore that is another thing we know. And by transitivity, if A determines B and B determines C, we know that according to that transitivity axioms of Armstrong axioms, we can derive another functional dependency that is A determines C. And this is the F closure. F closure means what? All possible dependencies, functional dependencies for a given situation. Okay. Is it clear or you have any doubts? Do you have any doubts about this? So what is F closure? Write down all the functional dependencies using the given details. Right? Now, this is not F closure. This is X closure. Okay. I will give you one more example for F closure. Right. Can you write down the F closure for this one? So we have A, B, C, and D. And we know that A determines B, B determines C, and A determines D. Okay. I write down F closure. You need to write down F closure. That is all functional dependencies that you can derive from this. Take 1 minute. I'm taking a lot of time for this one because these are the critical subjects for your future. Say you want to do a research degree. You want to be a critical thinker. What are the all the functional dependencies you can derive from this? By reflexivity, A determines A, B determines B, C determines C, D determines D. Then from given things, I can write A determines B, B determines C, and A determines D. And by transitivity, from these two, I can say A determines C. And can I say anything else? Can I say anything else? Nothing. That's all. That is my F closure. If you can tell anything else, let me know. But use only reflexivity and transitivity because if you use the other things, there can be so many other things also, right? අනිත් ඒවා combine කරන්න කිව්වොත් එහෙම මාට තව ලියන්න පුළුවන් but just concentrate on the first two only. Okay, first one. මොකද නැත්නම් මෙහෙම ලියන්න පුළුවන්. If A determines B, AC determines BC. So then you can say AC determines AC, right? From this augmentation. CD determines CD. එහෙම ලියන්න පුළුවන් දැන්. හරි. So forget about the other thing. Just concentrate on the basic two only. Okay, reflexivity and transitivity. Right. So then what is mean by exclosure? Now this question is you need to write exclosure. Exclosure means X means a particular attribute. F means all possible dependencies. X means all functional dependencies you can derive from a particular attribute. Now you need to write A closure, B closure, because X means any attribute. C closure, D closure, and E closure. Okay. So what is A closure? By reflexivity, A determines A. Right? A determines A. Do you agree? Because by reflectivity, A determines A. Now we use a slightly different notation because we need to write a lot of closures. Rather than I write A determines A, I just say A determines A. This is basically A determined A. And by this rule, A determined D. And by combining these two rules, if A determines D and D determines B, A determines B. If A determines B and B determines C, then A determines C, transitivity. So therefore, A closure is A, B, C, D. Do you agree? Or do you have any questions? So that is my A closure. That means A determines A, B, C, and D, but not T. Let's write B closure. By reflexivity, B determines B. And from here, we know that B determines C. And that's it. Nothing else I can tell because C doesn't determine anything. So then I can write C closure.
What is mean by uh, find X closure?
X closure means you need to write the dependency for each and every attribute. So which dependencies, functional dependencies A have, what functional dependencies B have, C, D, E. So you write dependencies for individual elements, not all possible dependencies. That is F closure. X closure means for each and every attribute, you need to write the functional dependencies separately.
Okay.
This is A closure, this is B closure. Now I'm into the C closure. By reflexivity, C determines C. Then there's nothing I can extract because C is not in the left side for any of these. So therefore, that's all. Then what about D closure? By reflexivity, D determines D. Then D determines B. So if D determines B, then D determines B. Then D determines B and B determines C means D determines C. And that's all. So therefore, D determines or D functionally determines D, B, and C or B, C, and D. So then I have E closure. By reflexivity, E determines E. Using this rule, E determines B also. And then B determines C. E determines B and B determines C means E determines C also. And C is not in the left side of anything. B is not in any other place. So therefore, that's it. So these are our X closures for this example. Okay.
So if we arrange it according to alphabetical order, is it
Yeah, that is fine.
correct?
Yeah, because this is like a set now. Order is not important, right?
Order. Okay.
Order is not important. Okay, so that is why I just kept it like that. Okay, order is not important. This is basically set. So E functionally determines these elements, individual elements. So this is the set. Okay. Right. So A determines ADBC, B determines BC, C determines C, D determines DBC, E determines EBC. Yes, that's it. Right. So now let's move on to, now we are going to apply. Now you know the theory. Atomicity, functional dependency, including Armstrong axioms. Now we can apply this theory, functional dependency theory, to better understand relational database designing or do the relational database designing in a much better, comfortable, confident manner. And if there are any issues, you can easily find those issues also because now you have better toolbox, right? Toolbox coming from relational theory. Right. So remember we use something called primary key. Primary key uniquely identify a record in a table. So every table must have a primary key. So then what is candidate key? Candidate key is a candidate for a primary key, right? So that is our casual definition we use. Candidate key is candidate for a primary key. That means candidate key must be able to uniquely identify a record in that table. So out of these candidate keys, we select one of the key as the primary key. Then other candidate keys are called alternate keys. Now we are going to define the meaning of the definition of candidate key using relational theory. Right. So candidate key is a minimum set of attributes that fully functionally determines all the attributes of that relation. So such a set of attributes is a candidate key, right? So that means your candidate key must fully functionally determines all the attributes of that relation. Okay. And it must be a minimum. It must be the minimum. So two words, right? Fully functionally determines all the attributes. And it must be minimum. So then it's a candidate key. So then out of those candidate keys, you can pick your primary key. Picking primary keys based on your other expectations and so on. Okay. Right. So let's take an example. So if you want to find all, now this is abstract, right? All of a sudden it is not employee, it is not student, it is not course. Now we are into abstract world of relational theory. Relational theory. Can you survive in this world? So then you can come back to the real world and be a better database designer with a lot of confidence. Right. So we have, say these are attributes A, B, C, D, and E. So these functional dependencies are given. First, you need to find exclusion. That means for each and every, find the closure. So then derive possible candidate keys using the definition given above. Okay, right. So let's find exclosures. Say A function determines A by reflexivity. A determines D. D determines B. B determines C, transitivity. Okay. But E is not in the left side of anything. Therefore, that's it. So therefore, this is my A closure. So is A candidate key? No. It is a candidate key if it functionally determines all the attributes, but E is missing. So therefore, A is not a candidate key. Let's take B. B closure. B functionally determines B by reflexivity. Then it says B determines C. And that's it. Because C is not in left-hand side anywhere. So therefore, B is not a candidate key. What about C closure? C determines C. And that's it. C is not a candidate. D. D determines D. And D determines B. And B determines C means D determines C. And that's it. So D is not a candidate key because we must have all A, B, C, D. Then what about E closure? E determines E. E determines B. B determines C. And that's it. So therefore, there is no single candidate key here. That means you can't take a single field and say, this is my candidate. This is a candidate key. Got it? Right. So remember, we need to find the minimal key or key combination that fully determines all your attributes. Now, because no single candidate key is there, now we need to look at composite candidate keys. And again, try to find the smallest. So if there's no single candidate key, see whether there's a two attribute candidate key. So can you find true attribute candidate key from here? I can see. I can see. Why? Because I know that no single value candidate key, atomic candidate key. Can someone tell me a possible multi-value candidate key from here by looking at these X closures? So if you include B also here, sorry, E also here, because E is only E is missing here. A, B, C, D, E is missing. So if you introduce E here, then E reflexivity E determines E. Now all of a sudden, AE combination functionally determines all these things. But if you introduce E here, it just add D here, right? So just by adding one value, it is not going to give all A, B, C, D, E here, right? Here D means A is not there, right? But here if I apply A, yes, then again it is same thing, right? A and A. So therefore it's the same thing. If I apply A here, then A is here. So then B is here, C is here, right? So then still do we have D? Yes, A determine D also. But anyway, that is the same candidate key, right? A. So therefore, what is the candidate key? The minimal key combination that fully determines all the given attributes, AE. So therefore, we have one candidate key, AE. Right? So then someone will ask, okay, what about then if we had few more here? Then make sure it is 2 or less. If you find another key which is having 3 attributes, then it is not a candidate key because candidate key must be minimal. Right? Minimal. Right? Minimum. So therefore, we have only one candidate key here, that is A. Right? That is A. Okay. A is the candidate because that is the minimum that gives you full functional dependence. Okay. Right. Any questions? So now we are done with the theory part. Now we are back into the database designing. Okay. Database designing means into the reality, not abstract ABC level. Okay. But normalization. So remember, normalization is a sequential thing. So you first look at the first normal form, and if it is already in the first normal form, you go to the second normal form, and if it is already second normal form, you think about third, and so on, right? You can't just skip and randomly take a normal form and check whether it is in that particular form, okay? Right. So what is meant by first normal form? So a table or relation is said to be in first normal form if all the attributes are atomic. Simple as that. At all the attributes must be atomic. If there's at least one attribute which is not atomic, your table is not in first normal form. Okay. If you find any non-atomic field, you need to take that field out and take it to a different table and create a one-to-many relationship with that. Right. So you find that there's a non-atomic field in your table. You take that field out and create another table, and then create a one-to-many relationship with that. That is the solution. The problem, the solution. Okay. So these are some examples. Right. So you must be just like a doctor, see the symptoms and identify the issue. You must be able to see if someone has designed this. You should be able to find out, okay, there's issue. Let's fix it. Right. Customer ID, name, contact numbers. You can see multiple contact numbers or possibility of multiple values. So that means this is not in first normal form. So this is not in first normal form. So you need to take this to a different table and create a one-to-many relationship. So what is the solution? You take this column from this table and create another table, like maybe you can call it customer contact numbers or whatever. So it can have its own primary key. Okay, maybe surrogated primary key. So then it's one-to-many relations. One customer can have many customer contact numbers. So therefore, foreign key goes to the foreign key is the customer ID, it goes to the many site. And same customer ID can have multiple. Now, rather than comma separated values, multiple value means multiple rows. So this can be duplicated because this is not your primary key. The primary key is contact ID, surrogated key, or something else. Right? So now a particular customer can have even 100 of contact numbers. Only thing is then 100 of records for that customer ID. Got it? So this is another example. Again, the solution is the same, right? Take colors into a separate table. Product colors, so some. So then corresponding to that product, you have the colors. So that means now Alto can have white, black, and blue colors. Maruti can have white and black. And in the future, if there's another color for Maruti, then there will be another product ID too, and that color comes. So this is the same issue in a different way, right? It's like same disease, different symptoms. So someone has designed it like this. Qualification 1, qualification 2. So now someone will say, okay, one qualification at a time. So this is atomic, but still this is not, actually this is not a solution. This is a false solution. False solution. Why? One way, if someone has 3 qualifications, now you are in trouble. Because we don't know how many qualifications someone can having. And the other thing is, if you had so many qualification columns, so then if someone has, most of the guys will have only 1 qualification, then you waste your storage. So therefore, this is not a solution. The original problem of atomicity is still there. So the solution is take this to a separate table. So that don't call it qualification 1, qualification 2. Okay. Same solution. Because it's the same problem with different symptoms. Right. Anything else you want to ask about first normal form and the solution? Right. So
I didn't understand the solution. Can you explain again?
yeah, the solution is we take it to we introduce another table. Say, so for example, say Alto product, say we have 3 colors of Alto cars in our showroom. Maruti, we have 2 colors. Panda, we have 1 color. Right? It can change in the future. Maybe Panda also we will get blue color. So therefore, this is now here single field have multiple values that violate first normal form or atomicity. Okay, because having multiple values is not a good idea because then you don't know what is the separator, right? After extracting data again, you need to subdivide these. Okay, an update can be really, right? Say you want to maybe add something, whether you should add it to the last or you need to check whether it is already there and so many things. So the solution is take this out, create another table. But in that table, you are not just keeping colors for that particular product. So that is why product ID is a foreign key. So Alto product, you can have white, black, blue, same thing, white, black, blue. But now those are 3 records. And here we have surrogated primary key. 1, 2, 3, 4, 5, 6, 7, 8. And for Maruti, product ID 2, you have white and black. And Panda, product ID 3, you have only white. So now, by combining these 2 tables, you know what colors are available for Alto, which colors are available for Maruti, and so on. Is it clear or it's not still clear?
Yes.
Okay. So the other thing is, in case, depending on color, if the price is vary, now what can you do? Can someone give me a solution? Say the black color Alto is Say blue color alto is more expensive than black color alto. Now what is your solution? Say black color alto is 30 million. Okay, 30 million is not realistic, right? Too much is, let's assume. But blue color alto is 35 million. So now what is your solution? Because those are the things that as a database designer, you need to take those decisions, right?
Create another table.
No, that is not a solution. That is unnecessary. Because price depends on color. Price depends on color. So then you can take this price column from here to here. So then say alto white, this price, alto black, this price, and so on. So you can take this price field from here to here. Because price depends on color. It's not the car has a price, but particular color, particular car with particular color has a price. Okay, right. Anyway, that is additional thing. Right. So now we move on to the second normal form. Now, if a table is in first normal form, only we look at whether it's in second normal form. Right. Second normal form says a relation is in 2NF if it is in 1NF and, right, that is why we say it's sequential. Every non-key attribute is dependent on the whole of the key, not part of it. Not part of it, whole of the key. In simple, we say no partial dependencies for the non-key fields. Okay, so this is more relevant when you have composite primary keys. So basically it says all your non-key attributes must depends on your primary key. Primary key. None of the attributes must not depends on primary key. And if it is a composite primary key, it must all your non-key attributes must depends on whole of the primary key, not just part of it. Whole of the primary key. If a particular attribute depends on part of it rather than whole, then it violates 2NF. If a particular attribute does not depends on the primary key, again it violates 2NF. Okay. So in case you find such a attribute which does not depends on your primary key or whole of your primary key, in case it's a composite key, you need to take that attribute to the relevant table. This is not the place to this attribute. So this attribute is in the wrong place. So it should go to the relevant table. Okay. If it depends on part of the primary key, right? So then if there's a table with that field as a primary key, this particular attribute must be a particular attribute in that table where that part is the primary. So that is called second normal form. So let's take an example. By the way, this first normal, second normal is in even A-level ICT. So don't think that this is rocket science, right? So we do the same thing for the A-level ICT student. But only thing is for A-level ICT students, we don't do this closure. We don't teach them the theory, but we teach them only the practical approach. But you guys, this is a degree program, so you have the theory at abstract level as well as application. Right, so let's take an example for second normal form. Say this is a table someone has designed. And it has a composite primary key, student ID, course ID combination, maybe connecting table of menu to menu. And it has two more attributes, payment and course name. Okay. Now, obviously it is in first normal form, no multi-valued value, non-atomic fields. So then you need to check whether this each and every non-attribute field, is it depending on the full primary key, right? Full primary key, not part of it, because it's a composite key. So payment, is it only depending on the student ID or is it only depending on the course ID? If so, it has violated second normal form. But if it depends on the combination of this, that is fine. So how do you explain this payment? Then you know the answer. What is this payment? So this payment is by particular student for a particular course. This 30,000 is student 1 for course 1. This is student 2 for course 1, 20,000. Student 2 has paid another 20,000 for course 2. So therefore, this is by particular student for a particular course. So that means this combination determines this, not individual thing. So that is fine. So that means it's not a partial dependency. It's a full dependency. This combination determines this. Or this payment is for this combination. So therefore, this attribute has not violated second normal form. This attribute is fine. Then what about course name? Is it determined by student ID, course ID combination or just one field? So basically course name is determined by course ID. Whenever it is C1, it is bit. Whenever it is C1, it is bit. So that means this depends on this, not combination of this. So therefore, this is a partial dependency. So course name should not be here. It's wrong. It has violated second normal form. Payment is fine. So what is the solution? So course name must go into a table where course ID is the primary key. So that should be the course table. You must have another table called course table and your course name must be there, not here. So that is the solution. Okay. Got it? So take the course name to the course table. If you already have a table or otherwise create a table. And get rid of course name from here. So now it is in second normal form. Okay. Right. Any question about second normal form? So I'm doing this very slowly because I know that this is something that shouldn't get struggle. In the very first day, I told you that the most challenging subject is database. You may not feel it like you will feel it when you go to the exam. Right? Because questions can be really challenging. You will be under tremendous pressure if you don't understand concepts. Right. So let's move on to the third normal form because there are no questions. Right. Again, you can check whether it's in third normal form only if you have already checked whether it's in first normal form and second normal form, and you have found that yes, it's in second normal form. Now you can check whether it's in third normal form. Right. So this is what third normal form says. The relation is in third normal form if it is in second normal form, and each non-key attribute field is directly depends on the primary key. In other words, no transitive dependencies. Second normal form, no partial dependencies. Third normal form, no transitive dependencies. Right? I will explain the solution, but let's take an example. Right. So this is a table called book. So there we have three fields, non-key fields. Now all your non-key fields must directly depends on the primary key. If so, it is in third normal form. But if it does not do like that. Rather, it depends on something else, and that something else depends on the primary key. So then we say there's a transitive dependence. Okay. So book ID determines book name. So there's no issue like that. So obviously, when you know book ID, you know the book name. So that is a direct dependence. Or your book name depends on book ID directly. So that is fine. Your book ID determines the publisher. Okay. Or publisher is determined by book ID, direct dependence. That is also fine. Then what about the contact number? This contact number is not the book's contact number, right? පොතකට contact number එකක් නැහැ. So this contact number must be what? Publisher's contact number. So that means publisher ID determines the contact number. So there's nothing called book has a contact number, right? This is publisher's contact number. Book determines the publisher, publisher determines the contact number. It's not book determines the contact number because there's nothing called contact number of a book. So that means we have transitive dependence. This determines this, and this non-key field determines this non-key field. So that is a transitive dependence. Of course, this depends on this, but not directly. Transitive. So if you have transitive dependency, it has violated the normal form. So therefore, this should not be here. This should not be here. So having publisher ID as a foreign key is okay, but this contact number should go into what? Publisher table, not here. So this is publisher's contact number. That is why every time your publisher is P1, contact number is this. So take it out and put it into the publisher table. That is the solution. Okay. So this contact number must be in the publisher table. So that solves the problem.
The non-transitive dependency means all the non-key attributes depend on the primary key.
Directly depends on the primary, not through another one.
Non-transitive means.
Yeah. So non-transitive means not transitive. Earlier transitive. Earlier contact number depends on publisher ID. Publisher ID depends on book ID. But now that we have eliminated, because now contact number depends on publisher ID, which is the primary key of that table. And publisher ID depends on book ID because one book has one publisher. That is fine. But having contact number here is the wrong thing. So that is why we took it to the correct table. Now both tables are in third normal form. So this violation is eliminated. Right. So usually in database designing, we care about first, second, and third. But there's something called 3.5 normal form and fourth normal form. But very rarely we care about those. Very, very rarely. Almost you don't care about it. But for your academic purpose, right, because it's mentioned in your syllabus, let's look at what is boycott normal form. Sometimes we call it 3.5 NF because this is in between 3 and 4. But these are very rarely we check. Okay. Anyway, we don't talk about the fourth normal form because sometimes if you try to do over normalization, it introduces, you can see every time when we do normalization, sometimes we need to introduce another table also, additional tables. So that means you need more and more joins in queries. So that will reduce the performance. So therefore, we don't want to do over normalization. But in case of a need, you must aware of there's something called 3.5, 4, and so on. But very rarely you don't need to worry about those. Okay. But anyway, we'll do 3.5 normal form. This is something in very specific situations only we need to check. Okay, very specific situations only. That is why most of the time you don't need to worry about 3.5. Okay, so what is 3.5 normal form or the boycott normal form says? Each attribute must represent a fact about the key, the whole key, and nothing but the key. I don't know whether you understand this. So each attribute must represent a fact about the key, the whole key, and nothing but the key. Okay. So no wonder it's good that we don't need to worry about 3.5 much, right? Because the definition itself is also really fuzzy. So let's take an example. Okay. Say we have table student. Says when we say student, let's say student ID, course ID, and instructor. Okay. So let's assume there's no other place instructor details are. There's nothing. There's no table called instructor. Okay. So that means for a particular student, for a particular course, we have assigned instructor. Say student 1, course 3, instructor is Nimali. Student 1, course 2, instructor is Nimali. Student 2, instructor, course 3, Nimali. Maybe student 2, course 2, again Nimali. So let's assume there's no table called, maybe there's another table called course, but there's no table. We keep data about instructors. This is the only table. Now, what is bad about this? So the obvious issue is, if there's an instructor who is not assigned to any student, then there is no information about that instructor. Because if there's a student and course combination only, that instructor's name is there. So therefore, if you have an instructor, still you have not assigned to any student, so that instructor's details are not anywhere. That is obvious. So therefore, this is not a good thing to do. So keep instructor details in the instructor table and get the foreign key, instructor ID here. Then it does not violate BCNF. Okay. It does not violate BCNF. Okay. This instructor and course. Anyway, this is a different solution actually. But anyway, the problem is obvious. The solution is not a very good one. Separate relation and become its key. Instructor. Yeah, this is thinking in different way. So correct. So that means if the instructor is assigned to a course, this way. But if the instructor can be assigned to different courses, so then another solution is take here you have the instructor ID and take instructor table separate. But this is a different solution, thinking in a different manner, okay? Because there can be different scenarios, okay? But anyway, this is not going to work. This violate BCNF, okay? This violate BCNF. Right. So now please move on to denormalization. So what is mean by denormalization? Shall we ask ChatGPT to generate another example for BCNF? Generate or give an example, table example for BCNF violation and solution. Now, how easy you guys to learn these days, right? Right. Now, what is the issue here? Course ID is not a super key, but it determines the instructor. Right. So again, they have take the instructor. Okay, that same issue. Right. Right. So then, what is the solution? Course ID and instructor here, and course ID, classroom, and time slot here. Yeah. So again, they have considered it's sort of a similar example. So they are assigning instructor to a course. Right. So then if student is following a particular course, so that course is for this particular instructor. But anyway, this is also not a very good example. So if you have instructor without course, again you are in trouble. So you can see that this is little bit controversial because different people interpret it in different way, right? Different way. But anyway, again they say having instructor here is not, anyway this is not assigning to a student. Okay, this is not assigning to a student. Okay, so therefore this is a different scenario. But what they say is because instructor is assigned to a course, right? Right. So therefore don't take it here. Don't take it here. But it's a different context of BCNF violation. Okay, different context of. By the way, usually we don't care about BCNF, and I have not seen a single question on BCNF in your exam questions. In the industry also, I have never ever encountered people talking about BCNF. Okay, BCNF because it's very fuzzy case and very special case. Okay, right. Yes, that is what I told you, right? BCNF is very fuzzy concept. Right? Very fussy concept because different people interpret it different way. So that is why I told you there's no single question on BCNF in exams. In the industry also, I have never seen anyone talk about BCNF because it's sometimes people go into more and more concept, right? So that is why these days people don't talk about BCNF anymore. Okay, very rare because it's very fussy. Right? Depends on uh, you look at it. Okay. So there's no single question about BCNF. I have never ever seen a BCNF question in your questions paper. So, well, okay. Right. So let's move on to the denormalization. So remember, the more you normalize, the more tables you introduce. Right. More table you introduce. But more tables you introduce means more joins in query. When you write SQL queries, that means rather than you take data from one table, two tables, sometimes you need to take data from two, three, four, five tables now because it's very highly normalized. Of course, that is good for the integrity and storage, but not very good in some cases for performance of queries. In that kind of a situation, although it violates normalization concepts, maybe we can take a particular fields to a different table. Ideally, it must be in B table, but we take it to the A table simply to increase the performance of the queries. That is something we do knowing the consequences. So that is called denormalization. Right? Denormalization. So we know that it violates the normal form, but still we take that to that particular table rather than to the proper table. So that is called denormalization. That is something we do very rarely, but especially when we have thousands and millions of data and otherwise the query performance is super low. So that is called denormalization. But that is we do knowing that what we are doing, right? Knowing what we are doing and for reasons. Okay. Right. So now we move on to our final topic. Features of good decomposition. Okay, so before doing the features of good decomposition, so let's do some past paper questions, okay? And then get back to this. Otherwise, it's theory, theory, theory. Okay. Right, some past paper questions. Can you do this question? 2022 question 37. Take 1 minute. It's a little bit fussy the way examiner has put it. Anyway, that is sometimes part and parcel of our life. Which of the following statements are true regarding data normalization? Multiple answers are possible. you can identify at least, if there are two answers, one answer, at least that is good. Right? Because some answers are fuzzy. The way examiners mention it. And which of the following statements these are true regarding data normalization? Answer 1. Helps to eliminate anomalies of the data. Remember, integrity. Anomalies means no integrity. Right? So when you do normalization, so we have better integrity because the fields are in the best place. Right? A particular field is in the very best place it should be. So therefore, I'll say yes. Help identify how to handle missing values. So missing values are again what? Integrity violations. Integrity violations. Okay. So in a way, examiners tell the same thing. Anyway, it's little bit fuzzy. That is why I told you, right? But anyway, missing values means integrity violations. Helps to get rid of inconsistencies of data. So inconsistency means again integrity. Because sometimes same value is multiple places because it's not properly normalized. Maybe you have multiple value fields and sometimes same value is in twice in your field with comma separation because it's not an atomic field. So I say yes. List suitable set of relations that support data requirements. So that means identify what are the correct tables for your requirements. Again, indirectly, yes. But it's more than identifying the tables. It is all about taking the correct field to the correct table. But anyway, for example, if it is non-atomic in first normal form, we introduce another table. So therefore, in a way, this is correct also. Right? So that is why I told you this is really fuzzy question and fuzzy answer. For example, when we do normalization, sometimes we identify, okay, there's a need for another table. So therefore, in a way, it's correct. But I think examiner has not taken this as answer. Right? It's a fuzzy, right? It's sort of opinionated. Right? Provide suitable means of storing data efficiently. That is not an answer because sometimes I told you when you do normalization, sometimes the efficiency is reduced. The more tables means more joins. Okay. So therefore, our objective of normalization is not to store efficiently or retrieve efficiently. It's it's all about duplication integrity. Right. So anyway, D could have been answer, but examiner has taken only ABC. Okay. ABC. Right. Do the second one. 2023 question 36. Consider relation EPQRSTU with following set of functional dependencies. Someone attempts to derive new functional dependencies from the above given set of propose the following. Set and propose the following. Which of the following statement is correct? So by analyzing these functional dependencies, someone has come up with three more dependencies. So the question is, which of these are correct? Or which of these can be derived from the given dependencies? And do it. So now you must be really comfortable with Armstrong axioms. So you can look at the Armstrong axioms and this there. What are the Armstrong axioms? A determines A, reflexivity. A determines B, and B determines C. We can say A determines C. Okay. So that is second one. Third one, if A determines BC, we can say A determines B and A determines C. If A determines B, then AC determines BC. ඔය එකක් තියෙනව නේද? ගණිතේ මතක නැහැ. නැත්නම් තියෙන්නේ. Other way. If A determines B and A determines C, A determines BC, AC determines BC. If A determines BC, A determines B and A determines C. හරි මේකත් හරි. මේකත් හරිනේ. If A determines B and A determines C, we can say A determines BC. දෙපැත්තට මේක හරි. දෙපැත්තට මේක හරි. So that means if A determines B, fifth one, B and A determines C, A determines BC. And may පැත්තට හරි මේ පැත්ත. If A determines BC, A determines B and A determines C. If A determines B and A determines C, we can say A determines BC. දැන් බලමු මේක දාලා කරන්න පුළුවන්ද කියලා. PR determines S. P determines R, P determines Q, right? So SC is in the right hand side only here. S දකුණු පැත්තේ ඉන්නේ මෙයා විතරයි. That means QR determines S. And this says PR determines S. No, right? Because P determines R. Say P determines R. So therefore PR also determines R. But there's no Q. Okay. Yeah, so I will not go for this. What about P determines T? P determines Q, Q determines T. So therefore, yes, P determines T. I will go for this. What about QR determines SU? QR determines U. Right? But it doesn't mean that QR determines SU. Right? So QRS determines SU, but not QR determines U, right? Therefore, I don't go for this one. Okay. But there's no answer, only two. No, we can win තව එකක් තියෙනවා විතර. Say QR determines this one, right? You can see QR determines S, QR determines U. If QR determines S and QR determines U, that means if A determines B and A determines C, A determines BC. If QR determines S and QR determines U, that means QR determines S and U. So therefore this is correct. මේ rule එක. ඒ rule එක A විදිහට තියෙන දැන් QR. QR determines S, QR determines U, therefore QR determines S. So therefore this is correct. So therefore I'll go for 2 and 3. Right? 2 and 3 means I'll go for C. Anyone got C? It's very challenging question, right? It's E. So that means 1 is also correct. So let's see whether 1 is correct. Maybe I have missed 1. So anyway, second and third are correct, but the answer sheet says 1 is also correct. But make a again. P determines the P determines Q. And also P determines P determines Q, right? Q. And QR determines, now remember P determines Q. Then Q and R determines S. P determines Q, Q and R determines S. So therefore, if I add P and R here, if P determines Q, P and R determines Q and R, right? So do you get it? Right? So let me explain it again. P determines Q, that is given. Right? P determines Q. Now using this particular rule, P and R determines Q and R. If A determines B, AC determines BC. දෙපැත්තටම එකම දේ දාන්න ඕන. මෙතනට R මෙතනට R. So then if P determines Q, yes, then PR determines QR. And here we know that QR determines S. So therefore, PR determines QR and QR determines S means what? PR determines S. Transitivity. බලන්න කොච්චර හිතන්න ඕනද කියලා කරා.
So can you explain the second one?
This
again?
one.
No, PR implies QR.
You mean referring to this one, last explanation?
Yes, sir.
Okay, so let me explain it from beginning again. Right, so we know that P determines R, that is given. Right, P determines R, that is given. But this is PR. So then I can say, remember this rule, if A determines B, AC determines BC, or AX determines BX. So therefore I will add R here, R here, because it can be anything. So therefore I can say PR determines, not PR, right? So S is QR, right? Yes. QR determines, P determines R. Yeah, so let's start from here. P determines Q. Okay, so we'll start from here. P determines Q. Okay, so if P determines Q, PR determines QR. Do you agree with that? That is, if A determines B, AX determines BX. So I add R here, R here. If P determines Q, PR determines QR. Because here also R, this rule. Okay. We have given that QR determines S. QR determines S. That is given. So if PR determines QR and QR determines S, that means PR determines S by transitivity. So therefore, this is correct. Is it clear now?
So that is mean by the fourth one.
This one.
No, by the fourth A.
If A determines B, AC determines BC. It's a rule, axiom.
The rule. According to that, it's true.
Yes, according to that. So that means we only use the axioms. Axioms and given dependencies. So you can't use anything else. So axioms and given dependencies, we can derive that PR determines S also, because P determines Q given. So that means PR determines QR by these axioms. And we again they have given that QR determines S. Then transitivity, that is A determines B and A determines C means A, B determines C means A determines C. So therefore PR determines S. So therefore answer is what? All. Right? All. So that is a very tricky question. Right? Very tricky question. Okay. Right. So let's move on to another question. This is easier question. Those abstract questions are always tricky. Okay. It doesn't mean to impossible. Sometimes you need to look at all these possibilities. But at the same time, you must only use axioms, right? Armstrong axioms, not something that comes to your mind. Right. Consider the given functional dependencies on the following relational schema. Which of the additional functional dependencies can be inferred, that means derived, from the above functional dependencies? And do it. Again, multiple answers are possible. So this really challenge you. When you are really challenged, only we can get the best out of you. Okay, so let's do it. So employee number determines this. Okay, well, let's again write down the axioms. A determine A determine B and B determine C means A determine C. A determine B and A determine C means A determine BC. If A determine BC, then we can say A determine B and A determine C. And if A determine B, then AC determines BC. On the rules, okay? Okay. Right. So let's take the first one. Employee number determines these three. Department number determines these two. So the first one, employee number determines department name, and manager number. Is it correct? So if you know the employee number, you know the department number, because employee number determines employee name and birth date and address and department number. Right? So that means if A determines BC, A determines B. So therefore, employee number determine department number. And department number determine department name and manager number. So therefore, this is correct, right? Because this determine this and this determine these two. So therefore, this determine these two. Second one, employee name determine. Now, that is not the case because this is in the right side. X determine Y doesn't mean Y determine X. This is employee number. There's from department name, you can't say anything like that because department name is not in the left side of anything. So therefore, we can't say like that. Just because you know the employee name, you can't talk about department now. Okay, because there can be multiple employees with same name. Right, employee name, department name. No, because employee name is in the right side. No, employee name is not in the left side. Okay. So employee number determine department number. Yes, you can see employee number determine department. If A determine B, C, A determine B, A determine C. Employee name, department number determine manager number. Remember, department number determines manager number. That is fine. But when department number is connected with employee name, it must be manager number and employee name, right? So we can't say that if A determines B, AC determines B. There's no such rule, right? Mem rule and so therefore, just because employee name and department number determine manager number, it doesn't mean employee name department number determines manager number. Because there can be another employee in the same department with the same name, but then that guy is in a different, sorry. But anyway, department number is there, right? If AB determines, if A determines B, but anyway, employee name is there. But anyway, department number determines manager number, right? So it looks like correct, but there's no axiom like that, right? This one, right? If A determine B, but there's no such thing, right? There's no such thing. If A determine department number determine manager number is correct. Then department number employee name. I don't know. My gut feeling says this is correct, but I can't find axiom for this. Okay, so let's keep it open and see what is the answer. Okay. Oh, this is not taken as answer. You can see there's no axiom to derive this. There is no axiom to derive this. That is why examiner has not taken this. But don't you feel like this looks correct? But what happens if employee can work in multiple departments? Right? Maybe same employee, but according to this employee number, right? But because I think this is because it's employee name, right? Not employee number. Right? So because there can be say Nimal department 5. Again Nimal department 3. So then it can be different manager number, right? Because Nimal department 5, Nimal department 3, Nimal work for 2 departments because we have not given any details about like that. Assuming like that, because same name, 2 employees. Anyway, this does not satisfy any of the axioms, so that is why I did not take it. But anyway, you can say examiner has also not taken it because this may not happen also. Right? Anyway, it's a very fussy question, but if you go by the axioms, answers are A and D only. A and D only. Okay. Right. So now let's move on to our final topic, features of good decomposition. Features of good and make sure you go through the UCSC note also. Okay. So let me open your UCSC note also. So to talk about the anomalies, possible anomalies, and what is meant by functional dependency. Right? Reflexivity, augmentation, transitivity. Notations. Projectivity, union. Right? That's it. Nothing, no explanation, nothing. So that is Armstrong axioms. Okay. So then what is first normal form, second normal form with some examples. Okay. So this is atomicity is not violated. Solution. In second normal form, no partial dependencies. Right. then solutions, then third normal form. Right? No transitive dependence. Non-key field cannot be, where is that? Non-key field cannot be a fact about another non-key field. එහෙම තමයි කියලා තියෙන්නේ. හරිද? මම ඔක කිව්වේ no transitive dependencies කියලා. Okay. And the further normalization like boycott normal form, those are not mentioned, right? Just they have mentioned that there's something called boycott normal form, fourth and fifth. Boycott they have given, එතනින් තමයි example එක අරන් තියෙන්නේ. හරි? Student course instructor. Okay. Mention කළ දෙනකොට ඔක අහලා නැහැ එකපාරක්වත්. හරි? And this is the solution they have given. ඒක තමයි ඔක උතනින් ඇවිල්ලා තියෙන්නේ. හරි? UCSC note එකේ example එක දැන් අරන් දෙන්න. හැබැයි මේකට එච්චරම හොඳ solution එකක් නන් නෙමෙයි. හරි? එච්චර හොඳ solution එකක් කියලා මට හිතෙන්නේ. හරි? So it could have been even better if you take instructor to a different table called instructor. Okay? Rather than now instructor is bound to instructor course and instructor student. Maybe, yeah, maybe this is also solution, assuming that the student table is separated there, course table is separated there. If those two tables are separated there, maybe this is a solution. That is, instructor is bound to course and instructor is bound to, I think that is the assumption. So the assumption should be, you have a separate instructor table. You have a separate course table. You have a separate student table. In addition to that, we have these two tables, where instructor is assigned to courses and instructor is assigned to students. So instructor can be assigned to many courses, course can have many instructors, and instructor can be assigned to many students, maybe student can be assigned to many instructor. Maybe that kind of a thing is in mind when this kind of a table is designed. Okay? Because without any context, we can't say exactly what is the exact solution. The exact solution depends on your context. That is why it's very difficult to understand what is the solution is. Okay? But definitely there's an issue here. There's issue here because if there's instructor who is not assigned to any student or any course, then that details are missing. Okay? So that issue is there, but the solution depends on right context. Okay. You can see if we need to add an instructor Silva for database, we have to wait till an appropriate student is present. Right? Unless there's a student assigned to the instructor, you can't add details about the instructor. That is the problem. That is the problem here. But in reality, there can be instructors who are not assigned to the students, but we need to keep that. So that is a problem. Problem is very clear, but the solution depends on how you relate instructor to other tables. Okay, so that is why there are different possible solutions. Okay, right. Right. So in your note, they have not mentioned about decomposition, but in past papers, they have asked these questions. Okay. So that is why I'm doing this topic. Okay. So this last subtopic, that is features of good decomposition. So this is not directly mentioned in your note, but they have asked questions. Okay. So therefore, let's do it because this is another standard topic in database normalization. So therefore, whether it's mentioned in your note or not, I want to do it. So that you are perfectly, we cover everything in normalization. Okay. Right. Features of good decomposition. So there are two concepts related to this. Lossless decomposition, preserve dependencies. Okay, lossless decomposition. What is meant by lossless decomposition? What is meant by preserving dependencies? Okay, so preserve dependencies, we are not going to cover because that is another aspect. So we only look at the lossless. Okay, you can make a tawat කැලක් නොකර තමයි අපි මේ කරන්නේ. මොකද මේ කැලක් ඔයගේ සිලබස් එකේ කෙලිම තියලා නැහැ. Right. So let's see what is mean by lossless decomposition. Decomposition means break it into parts. Okay. So when you decompose a table into multiple tables, there are two possibilities: lossless decomposition, lossy decomposition. So lossless means when you break it into, say, multiple tables, say two tables, we can generate the same data without any issue by joining these two tables. By joining those two tables, we get all the details of the original table. So then we say lossless. So that is good. So that is what we want to do. Lossy decomposition means when you break it into two tables, you can't join these two tables and get all the information in the original table. So that means you have done a mistake. Your decomposition is not good. It's lossy. It's lossy. So every time you break a table into multiple tables, you need to make sure that you break it in a lossless manner. Otherwise, you destroy your data integrity.
So what is the context here? Data or something?
Sorry?
What is the context?
Breaking tables into multiple tables. Breaking a table into, say, single table into multiple table. So that is what
Okay,
we
sir.
have been doing, right? In normalization also, sometimes this table, we introduce another table. Now all of a sudden, rather than one table, now we have two tables, three tables. Okay. So when you break tables into multiple tables, so this topic is all about make sure your new tables are lossless. That means after breaking it to multiple tables, still you can create that original data set from the original table of the original table. If not, that means your new table structure or the relationships are not preserving the integrity of the data. That means we can't get the original data. Okay. Right. So lossless if it is possible to construct the relation R using joins, exact records. Lossy if it results in loss of information when joining the decomposed relations. Okay. So that means either some data is missing or ambiguity. We don't know exactly whether the student belong to this course or that course now. But earlier we specifically knew this student belonged to that course. But now by joining, we don't know which student belong to which course. That means there's a loss of integrity. So let's take an example, okay? Right. So this is a table. For some reason, maybe during the normalization process, some designer may have break it into these two tables. So original table, the new two tables. Okay. So original table has employee ID, name, project name, and project location. So here name and project location in one table, employee ID, project name, and project location in another table. Okay. By look of it, you can see that this is not a very good way of doing, right? But you must be able to explain why this is not a good decomposition. Now, this is original data. Right? So there are three employees, Nimal, Amal, and Kamal. Nimal work for project 1, Amal work for project 2, Kamal work for project 3. And project 1 is in Colombo, project 2 is in Colombo, project 3 is in Canada. There can be some other records. Okay. Now, what is wrong with this decomposition? Can you explain the issue when you have this kind of a two tables structure? By looking at the data, you should be able to explain the issue. Now your foreign key is something like project location, not something like actual project location, right? And this table also, possibly a project location is a foreign key. But at the same time, none of the table project location is the primary key also, right? So you can see that this is a bad thing. Of course, this is a bad thing. That is why this is lossy. Right. Now, if you try to join, now obviously if you join, you need to use this common column. You need a common column to join. But now you can see Nimal, Colombo, you have two projects. So then we don't know whether Nimal belong to project 1 or project 2. But here we know that Nimal belong to project 1. And just project 1 happened to be in Colombo. But now we know that Nimal is in Colombo. But Colombo, there are two projects. Earlier we knew that exactly Nimal belonged to project 1. But now we don't know whether Nimal belong to project 1 or project 2. That means it's lossy. You don't have the same view as previous. By looking at the data through these two tables, we get a different view. Now what we can say is Nimal is either working for project 1 or project 2. But in reality, Nimal used to work in project 1. So that means these two are having now two different views of data. So that means this is not going to represent this. There's something integrity issue here. Therefore, this is a lossy decomposition. Okay. I hope you got the issue. Right. So now you can see that if you join it, this is the result. So that means now we don't know whether Nimal work for project 1 or project 2. Whether Amal work for project 1 or project 2. But earlier we knew that Amal work for project 2. So therefore, this is not going to work. This is a bad decomposition. Okay, bad decomposition. Lossy decomposition. Right. So how to determine that? That is by just looking at we determine, right? Without any theory. Now, if you have a better theory, that is good. Right. You do that so that we can confidently determine whether it's lossy or not. Right. So this is a little bit of theory. How to determine if a decomposition is lossless or lossy. Okay. So there are three conditions. Okay. So consider a relation R is decomposed into two sub-relations R1 and R2. Then, if all the following conditions satisfy, then the decomposition is lossless. If any of these conditions fails, then the decomposition is lossy. So that means you need to check following three conditions. If all three conditions are satisfied, it is lossless. If at least one condition is failed, it is lossy. Okay. Now we'll take the three conditions. Super easy conditions. First condition, union of both the sub-relations, if you have three tables, all three, must contain all the attributes that are presented in the original relation R. So when you take the union of your subtables, table 1, table 2, table 3, it must have all the attributes of the original table. That is common sense. Right? Common sense. Otherwise, you have missed some columns. එහෙම නැත්නම් අර original table එකේ තියෙච්ච column එකක් හලලා දැන්. ඒතකොට ඒ column එකේ තියෙච්ච data නෑ. So this is not rocket science, right? This is common sense. So union of your newly created relations must have all the fields of the original relation. If not, it's lossy. You have lost some fields in your new tables. I think that need not any more explanation. Okay. Right. Condition 2. Intersection of the two sub-relation, as we break it into two, must not be null. So when you break it into two tables, there must be at least one common attribute for those two tables. Otherwise, we can't join. Common sense. Common sense. Right? Say earlier you had these attribute 1, attribute 2, attribute 3, attribute 4. Now you break it into like this. Attribute 1 and attribute 2 here, attribute 3 and attribute 4 here. Now how can you join this? Now earlier you knew that for this, say A, X, Y, A, B, C, D. Now A and B is here. C and D is here, but there are other records also. Now, how do you connect this? Because there is no common column. Without common column, we can't join. So again, that is not rocket science, right? So that is 100% common sense. So if your newly created tables, if it doesn't have any common field, definitely that's the end of the story. It's losing. Now you can't join this and create these records as it is. Super easy, right? Super easy. Super easy. Right. What about the third condition? I mean, become common sense and that is why I added it. So the third condition says intersection of both the subrelations must be a super key of the at least one R1 no R2. So when you take the intersection of your two relations, right, that is intersection means common fields. Right? Say here you have A, B, C. Here you have A, C, D. Sorry, let's say A, B, C, A, B, D. Now we have common columns, right? Therefore, R1 intersection R2 is what? A and B. Let's say this is my original table. It had A, B, C, D. Now we have A, B, C and A, B, D. So the intersection must be super key of R1 or R2 or both. So this is our intersection. So that means this intersection must be a super key of either this one or that one or both. So let's say this one's primary key is AB. Then that is satisfied because this is a super key of this. Super key කියන්නේ තමනුත් අයිති. Okay. It must be either super key of this one or that one or both. So then this is lossless. Okay, let's take an example. Right. So consider the sorry.
Could you explain the condition 2 again?
Condition 2. That means
Yes.
there must be at least one common field. When you break it, so when you break it, your A, B, C, D fields. So if you break it like this, here you have A, B, here you have C, D. There is no common field here because A is not here, B is not here, C is not here, D is not here. So that means it has violated this because then R1 intersection R2 is 5. But if you break it like A, B and C here and C and D here, that is 5 because C is common. That is common sense, right? If without a common field, you can't join this. Is it clear?
Yes, sir.
Right? So there must be at least one attribute which is common to both tables. Otherwise, you can't join. Simple as that. Okay. Right. So now let's take an example. Consider relation schema R, A, B, C, D with the functional dependencies A determine B. That means A determine B and C determine D. Determine whether the decomposition of R into A, B and C, D is lossless or lossy. Now someone is planning to break this as A and B here and C and D here. And the question is it okay? This is the original table. Right? A, B, C, D. Actually, by look of it, you know that this is not going to work, right? Why? What is the reason? Is it going to satisfy condition 1? Yes. Because you have all the fields. So union, what is condition 2? R1 union R2 must be R, yes. Union of A, B and C, D is A, B, C, D, yes. But condition 2, R1 intersection R2 must not be 5, but here R1 intersection R2 is 5. There's no common field. But before looking at that, you need to look at these functional dependencies also. Right? A determines B, C determines D. So that means A determines B, C determines D. That means possibly A and C are primary keys. Okay. Okay, so let's look at the answer in formal manner. Condition 1 is okay because your union has all the fields in the first one. But this one is empty. So therefore, there's no way we can join. There's no way we can join and get data. So therefore, this is lossy. You don't need to check the third condition because second condition is fair. Right. So look at this one. This time, this is the decomposition. A, B, C, this original. So someone has decided, okay, let's go like this. A, B, and AC. So again, you need to check these three conditions. Okay. Lossless or lossy. So obviously the first condition is satisfied, right? AB and union AC is ABC, yes. What about condition 2? Condition 2 is also satisfied. There's a intersection is A, it's not empty. Not empty. Third condition, what the third condition says? Its intersection must be a super key of one of these or both. Right? One of these or both. So remember, A determines B means A is the primary key because from A you can find B. And intersection is also A. Intersection is A. So therefore, this is, and A can be a primary key, right? Super key කිව්වම ඒකට අමතරව තියුණත් කමක් නැහැ. නමුත් primary key එක super key එක. Right? So this is A and B, this is A and C. And A determine B. Of course, A does not determine C, but A determine B. Right? So therefore, it satisfies third condition because A is a super key of this relation. If it is a super key of at least one sub-relation, that is fine. Right? A can be determine all the attribute of sub-relation because they have given that A determine B. So therefore, A is a primary key. And common field is also the primary key. So therefore, that is done. Condition 3 is satisfied. So therefore, it's a lossless breakup. Okay. Right. So this is little bit more complicated example. Okay. Little bit more complicated example, but it's good for your confidence, right? Your logical thinking and so on. So this time we have 4 attributes in one table. And these are the related dependencies. Someone has decided to break it into 3 sub-relations. 3 sub-relations. Now you want to check whether is it lossless or lossy. Already we know that A determine B, B determine C, C determine D, and D determine B. Right? Now let's take condition one by one. Right? So how they have taken it? A, B, B, C, and B, D. A, B, B, C, and B, D. Now A, B, B, C, and B, D. But you can't take all 3 and do this check. So therefore, you need to take 2 by 2. So therefore, let's assume these 2 we consider it as one particular relation for the time being, intermediate solution. Because we can compare only 2 at a time. Because AB and BC, we can say ABC. And let's first look at whether if someone break it like this, is it okay? Is it okay? If it is okay, if it is not okay, that's the end of the story. If it is okay, then we need to check. If you break it like this, is it okay? So it is also okay, then this is okay. Right? So that is the idea. Okay. Right. So therefore, let's assume someone has first break it like this. And let's see whether is it going to work. A, B, C, and B, C, and you can see there's a common field. All the fields are there. Right? So condition 1 and condition 2 is obviously satisfied, right? A, B, C, D, all the fields are there. And there's a common field right? Not intersection is not 5. Now you want to see the third condition. Okay, let's use our slides. Right. So remember, we are in the intermediate level, A, B, C, and B, D. So the first condition satisfied, second condition satisfied. Okay, let's look at the third condition. Right. So remember, so these are our, so we have A, B, C here. Right. A, B, C here. Because we have taken these two together, and B, D here. Right. And our common field is now what? B. Common field is B. Now let's see whether if B is a super key of either this table or that table. Right. So therefore, let's take B closure because B is a common field. Right. And remember, B determines C. B determines C. And C determines D. And D determines B. Okay. D determines B. And A determines B. Right. So remember, A determines B, B determines C, and C determines D. D is not here, and D determines B. Okay. So therefore, what is B closure? B closure. B determines B by reflexivity, and B determines C. And because C determines D, B determines D. And D determines B, already B is there. So therefore, B determines B, C, and D. If B determines B, C, and D, you can see that B is a possible super key here. Because B functionally determines all the fields in this table. Because B determines B, B determines D. So therefore, B is a super key of this table. It is not a super key of this table because you can see A is not here, there. But remember, if it is super key of at least one table, that is good enough. So therefore, B is a super key of this table because B determine B and D, right? C is not relevant. So therefore, third condition is also satisfied for this intermediate division. This intermediate division. Because B determines B, C, D. So now we are done up to this point. But actually, then you need to look at the next level of, because ultimately we have three tables. But assuming that we initially divide like this, that is fine. Okay. Now you want to look at whether this is correct. A, B, and B, C. Right? A, B, and B, C. Because that is our real tables. And again, intersection is when you connect all these things, you get ABC. And ABC, that is fine. Condition 1, fine. Condition 2, yes, we have common field. Second condition satisfied. Third one, right? Third one. So, is your intersection super key of any of these two tables? Right? So our intersection field is now what? B. Let's find B's closure. If B closure is containing either C or A, we are done. Okay, so let's look at the conditions again. So B determine C. Of course, B determine B by reflexivity. And here we know that B determines C. And that is fine. So that means B is a super key of this. Actually, B is a primary key of this also. But can we say that B determine D also because C determine D, and again D determine B. That's it. But B does not determine A. Remember, B is our common field now, but B is not a prime super key of this, but it is a super key of this. So that is good enough. Just if it is a super key of at least one table, that is good enough. So therefore, this is also fine. So therefore, this decomposition is lossless. This decomposition is lossless. Okay. Remember, B closure is BCD. BCG, which is super key of the second table. Attribute B can determine all the attributes of the subrelation R2. Thus, it is a super key of the subrelation R2, R1, R2, R3. So therefore, this is fine. Got it? On normalization, I ඉතුරුවක් වැඩි කරේ නෑ චුට්ටක් ඉතුරු කරා. ඒ තමයි මොකද්ද? ඒ කරන්න ගියොත් එතන තවත් වැඩි. Preserve dependencies කියන එක ඉතුරු කරා. මොකද ඒක කරන්න ගියොත් තව වෙලා යනවා. But yeah, lossless කියන එක මම ඔන්න explain කරා. හරි? Lossless ඒවා සමහර past papers වල තියෙනවා. And it's very easy concept, right? මේවා තේරුම් ගත්තම හරි interesting, lazy concept තේරුම් ගන්න අමාරුයි. Right, so that's it. That's it. Right, so we are done with normalization. Normalization.